Okay, so I'm gonna begin this discussion. We're gonna cover two problems of the energy equation and two problems on velocity fields and I guess the differential versions of the Reynolds transfer theorems. So let's begin. So here we have an example problem. We have gasoline at 20 degrees Celsius. It's being pumped through this smooth 12 centimeter diameter pipe that is 10 kilometers long. We're given that the flow rate through this pipe is at 75 cubic meters per hour. At the inlet of our pipe, there's a pump that is providing a pressure of 24 atmospheres. And at the exit of the pipe, we have standard atmosphere being applied. And the location at the second point is 150 meters higher than the first point. We're interested in finding the frictional head loss, and we want to compare that term to our velocity head. So I guess to quickly go back and recapitulate what's going on, we have Bernoulli's equation, which we've been working with last week. And Bernoulli's equation essentially says that the three energy term, internal energy, kinetic energy, and potential energy, combines to be our total energy, value. And as long as we're in the same streamline location with some other assumptions, such as steady state, incompressible, inviscid, as long as it's in the same streamline location, this total energy value will not change as long as you sum of those three terms. However, now we want to expand on that and say that if there were changes in energies occurring between point 1 and point 2 in your streamline, we can now account for those, and that's how the energy equation comes to be. So once again, with Bernoulli's, it is pressure, internal energy, plus kinetic energy, 1/2 rho v squared, plus internal energy, rho gh. It's equal to some constant energy term anywhere along your streamline. But now for our energy equation, we're now going to take all these terms. First of all, we're going to convert them to head, which refers to essentially height of fluid column. That's what it represents. If you were to look at those like manometers and those kind of tools. And once again, of course, now we consider the fact that the total energy value can be changing as you go along points 1, point 2, etc. So energy equation. So we have our inlet. I guess you get a pick, but for me, 1 is inlet. So for inlet, we have pressure divided by rho g, which is specific weight. We have kinetic energy, v squared over 2g, alpha. That's right, there's alpha in front of this. This is your velocity head values, plus z, which is current height you're at. So we just basically divide the entire Bernoulli's by rho g. Is what we did. So for our inlet is equal to pressure divided by rho g plus alpha v squared over 2g plus z for location 2, which is our outlet. And so hypothetically, let's say there's a pump sitting in between points 1 and point 2. This pump would provide additional energy, so point 1 would then get additional energy. So therefore, point 2 would have more energy than point 1. To consider this factor of the pump, we're going to subtract by height of the fluid column of the pump to account for the fact that with a pump, at the fluid at location 2 will have more energy than fluid at location 1. So on the other hand, if there was a turbine that is using the fluid from section 1 to generate power and divert the power somewhere else, or if there's friction occurring as you go from point 1 to point 2, the turbine and friction cause loss at point 2, which means that point 2 would be less energy than point 1 due to these two components or contraptions. Therefore, we have to add the energy back to maintain this energy balance. So once again, we add fluid height column of turbine and height of friction, or head of friction, which is head loss, essentially. And speaking of head loss, that's what we're trying to find. And we want to compare it to velocity head, which is, I guess, v head. But all v head is v squared over 2g. Okay. Any questions on the definition of Bernoulli's or energy equations? Anything like that? Okay, if not, let's jump to our find given. Let's talk about our givens. So we're given a lot of different variables. Let me write them down for us. Okay, we're given that once we're working with oil, once again, going through this pipe, we're given that the density of oil 680 kilograms per cubic meter. We're told that the diameter of the pipe is 12 centimeters, so 0.12 meters. Told that the length of the pipe is 10 kilometers. We're given volumetric flow rate, 75 cubic meters per hour. If we want to convert to cubic meters per second, we divide by 3,600, which gives us 0.02083 cubic meters per second. We're told that the pressure at the inlet given by the pump is equal to 24 atmosphere. 1 atmosphere is 101 kilopascals. Therefore, we have pressure by the pump is 2,424 kilopascals. Pressure at the outlet is 1 atmosphere, 101 kilopascals. And we're told that at location 2, we are 150 meters higher than location 1. If we let location 1 be our datum, which means Z1 equals 0, then Z2 is just equal to 150 meters. Okay, so let me get the energy equation real quick. And we're going to try to simplify it down so it'll be easier to work with. Bless you. So first off, once again, datum is Z1, therefore Z1 cancels out. There's no turbine at all, so we cancel that zero. That turns to 0. And interestingly enough, H pump is also 0. The reason why H pump is 0, despite there being a pump in our schematic, is that the pump in the schematic is not between locations 1 and 2. It is before location 1. The pump provides the pressure that drives the flow from location 1 to location 2. But because it's before location 1, we do not have to account for it in our energy balance equation. In fact, P pump is just P1 because location 1 is right in front of the pump. And the last thing I want to mention is that we're given that the volumetric flow rate for the oil is as it goes through the pipe is 75 cubic meters per hour. And so that's the volumetric flow rate through the pipe. And given that our pipe has a constant cross-sectional area, we can also assume constant velocity between point 1 and point 2 because the flow being driven is steady at that same speed. Therefore, when we do the energy balance equation, we'll see that the velocities will also cancel out. In regard to the alpha term in front of the velocity head term, I'll talk about that more in the next problem. Okay, so as I mentioned before, we have constant volumetric flow rate and constant cross-sectional area. Therefore, we have constant velocity. Volumetric flow rate is velocity times area. Therefore, velocity is volumetric flow rate per area. Volumetric flow rate we have is 0.02083 cubic meters per second. Area is pi over 4 times diameter squared. Diameter is 0.12 meters, and we're going to square that. Therefore, we get 1.84 meters per second. So that's your velocity going through the system. Let's solve for velocity head first, because again, we have all the components to do so. Velocity head is v squared over 2g, and it's, I guess, so 1.84 meters per second. We just gotta square that. Divide by 2 times gravitational acceleration constant, 9.8 meters per second squared. Therefore, we get a velocity head of 0.173 meters. So that's your velocity head, and this is the value we're going to compare our head loss to, which is due to friction, obviously. One thing I quickly forgot to mention, I'm going to quickly mention now, our assumptions. So in Bernoulli's, we have 4 assumptions. We assume steady state, inviscid, incompressible, and a long streamline. I guess also there's no work being done or no heat transfer going on as well. To be fair, that's the 5th underlying assumption for Bernoulli's. But for energy equation, there's only 3 assumptions: steady state, incompressible, and a long streamline. We don't assume this anymore because we have the alpha term, which I'll say more about later, as well as the fact that we do factor in head loss now, so which is partially due to friction. Okay, so given the equation, this equation here, we're now going to simplify it down. Left-hand side, all I have is pressure pump divided by rho g is equal to right-hand side, so pressure of the exit, P2, which is 1 atmosphere, by the way, divided by rho g, plus Z2, which is the difference in height between locations 2 and 1, plus head loss due to friction. I'm going to isolate for the head loss due to friction. So H friction is equal to P pump minus P2 divided by rho g plus Z2. Sorry, minus Z2. Okay, so now I'm plugging these values and get an answer. P pump was 2,424 kilopascals minus 101 kilopascals. Make sure I multiply by 1,000 to go from kilo to just normal pascals. Divided by rho g. Density was 680 kilograms per cubic meter for oil times gravitational acceleration, 9.8 meters per second squared, and everything afterwards subtracted by 150 meters for the difference in height. Therefore, H friction should be (198 meters). So that is your head loss, which is based on a fluid column height. So if we look at that value, head loss and velocity head, you see that it's nearly a factor of 1,000 off of one another. So head loss is over 1,000 times more than the velocity head. And if we think about oil going through the pipe, the oil is probably slushing through the pipe, very low velocities, and oil is very viscid, so a lot of head loss or friction is occurring, flowing down the oil. So, and given, once again, also the fact that the pipe is 10 kilometers long, it explains why the head loss is much, much greater than the velocity head. Any questions on this example? Okay. If not, we're going to do the same concept, but for a different problem. Let's go back to water. So here in this problem, or example, I guess, we have a pump, and the pump is delivering water from a reservoir to a machine that needs it. So the pump delivers this water at a volumetric flow rate of 1.5 cubic meters per second. We're told the machine is located 20 feet higher than the reservoir, and reservoir surface, I should mention. And we're given that the loss between points 1 and 2, which is head loss or head loss due to friction, we're given it as a ratio of velocity head, or I guess a multiplier, a factor of velocity head, sorry. And so this factor is K, and we're told that basically head loss is 7.5 times the velocity head value, much less than 1,000, which is what we saw earlier. And now here, we're also given that alpha, which is now, I guess I mentioned, the term that goes in front of the velocity head term, alpha is 1.07. And so basically with all these terms, we want to figure out what the horsepower is required for the pump to essentially do its job, its purpose, given the fact that the pump is working at 80% efficiency. So let me copy that energy term real quick first. Maybe I have it already. Okay, so quickly just talking, that, I should say schematic. So the alpha term you see there, this is your kinetic correction factor, and obviously it's the correction factor for your kinetic energy term, which is your velocity head. So this alpha term, the reason why it exists is due to the fact that when in pipe flow, you're going to have some kind of velocity profile, velocity distribution of the fluid as it goes through the pipe. whether it be fully developed as a parabolic flow through your pipe, or maybe it's currently developing and it looks something more like this. So the alpha term is meant to correct for that and get basically the mean velocity that's going through your pipe, because we can't really assume 1D inlet outlet all the time. That's why the alpha term exists. So one thing to note that I mistakenly told the other classes is when we look at laminar and fully developed flow, which is the left image you see there, alpha approaches 2.0. So alpha goes to 2.0 when you have laminar and fully developed flow. For nearly fully turbulent, or basically fully turbulent flows, your alpha returns to 1, and you basically get back Bernoulli's equation when alpha goes to 1. So that's actually the difference between the two. Laminar and fully developed flow, your velocity distribution gets you an alpha of 2. Otherwise, with fully turbulent, alpha goes back to 1. And that's due to us trying to calculate the mean velocity for that entire profile. Okay, back to the energy equation. Let's talk about givens. Maybe find first. We're interested in finding power of the pump. Okay, what are we given? So we're working with water, so density is 94 slugs per cubic feet, which also implies that your specific weight is going to be 62.4 pound force per cubic feet. Given the volumetric flow rate is 1.5 cubic feet per second. We're also assigned the Z1, which is where the reservoir surface is located, is equal to 0. That's going to be our theta. Which also means that Z2, which is the machine, we're told that's 20 feet higher than 0.1. Therefore, Z2 is 20 feet. Okay. Pressure, so P1, pressure at the reservoir surface. The reservoir surface is sitting right underneath the atmosphere. Therefore, it experiences atmospheric pressure only. 1 atmosphere in BG units is 14.7 psi, pound force per inch squared. P2, pressure right before the fluid enters the machine, is 10 psi, so pound force per inch squared. Finally, we're told that the diameter of the pipe which the pump pushes the fluid from the reservoir into the machine, that diameter is 3 inches. So, given our energy equation, let's try to simplify as much as we can in order to work with a simpler form. So once again, our theta is Z1. Z1 can be 0. There's no turbine in our system. Get rid of that. But we do have a pump in between locations 1 and 2 now. So we got to consider H pump and H friction head loss. That's gonna be there always. I think that's it. Okay. So now I'm going to start isolating for H pump because that's what we're interested. H pump, fluid head column of the pump, which will eventually give us power of the pump. So left-hand side of the equation. Oh, sorry, one more term I forgot to remove. Location 1, that's the reservoir surface. Reservoir surface is hydrostatics. There's no fluid moving. Therefore, velocity head at the location 1 is also 0. So left-hand side of the equation, we're given just the pressure term of the reservoir, so atmospheric pressure divided by rho g. Rho g we're going to represent as a gamma for a specific weight. It's equal to pressure location 2 divided by gamma plus alpha kinetic energy correction factor times velocity head, v2 squared divided by 2g, plus z2 for the height difference between locations 2 and 1, minus h pump, plus h friction. Oh, sorry. I think it's given, once again, h friction can be represented as a factor of velocity head, which is k. So k times velocity head. And that's given in the statement here. Okay. So once again, I'm isolating for H pump. I'm going to move H pump over to the left-hand side and move the pressure P1 term to the right-hand side. So H pumps equals P2 minus P1 divided by gamma. Plus, I'm going to combine these two velocity head terms. Alpha plus K times V2 squared divided by 2G plus Z2. So this is my equation for H pump. And I have every term but V2, which I'm going to solve for right now because similar to the first problem, we have a volumetric flow rate, we have constant cross-sectional area in the pipe, therefore we can solve for velocity. Q is VA, V is Q over A, Q is 1.5 cubic feet per second, area is pi over 4 times diameter, I believe it was 3 inches, so 3 over 12 feet squared. That gives me 30.6 feet per second. That's the speed of the fluid, thanks to the pump. I can now plug in my values to get H pump. H pump equal to P2. That's machine. Yes. Okay. 10 psi, pound inch squared, minus atmospheric pressure, 14.7 pound force inch squared. We're going to convert to from inch squared to feet squared. 144 inch squared over feet squared. Divide by specific weight, 62.4 pound force per cubic feet, plus combination of kinetic energy correction factor and factor of head loss based on factor of velocity head. So 1.07 plus 7.5 times v squared, it's up here, V2, 30.6 feet per second squared, divide by 2g's. For BG units, acceleration of gravity is 32.2 plus 20 feet for the difference in height. Therefore, H pump is equal to okay, so I get 133.8 feet. That's my, if I represent the power of the pump based on, or I guess pressure of the pump if I represent the pressure of the pump using fluid column height, it would be 133.8 feet. So now we want to find the power of the pump in order to, or the power that the pump should provide in order to move the fluid, or sorry, the power required to move the fluid from the reservoir to the machine. Here's how we're going to do that. So the energy equation, in terms of energy, and I should specify potential energy. Potential energy is mass times gravity, acceleration times height. That's potential energy. Power, we can look at power uppercase. Power as time derivative of energy, in our case, potential energy. G is constant, gravitational constant. H, our height, is constant as well. Only thing that is changing in this system, or in this problem with fluids, is your mass. Your mass can turn to mass flow rate. Therefore, power can be represented as mass flow rate times gravitational acceleration times height. So, with that in mind, we can represent P pump, power of the pump, as mass flow rate times acceleration of gravity times height, fluid column height, representative of the pump. And so usually you actually break this down. So mass flow rate is rho Q, volumetric flow rate times with density, rho Q G times H pump. Maybe I should draw. But rho G together gives you specific weight. So it's volumetric flow rate times specific weight times fluid head column of the pump. That's the equation for power. And this also applies to turbines as well. Now, we're going to plug in our values and solve for power required by the pump. power pump is equal to Q, 1.5 cubic feet per second, gamma, 62.4 pound force per cubic feet, times fluid height column of the pump, 133.8 feet. One thing to notice here is you would see the cubic feet cancel out, and what we're left with is pound force times feet. You know, it's kind of like force times distance, which is work. Work is energy. Energy per time, second. So, which is power, essentially. So we maintain the units of power, which is good. And this would get us 12,500 and, keep that, 500 pound force per feet per second. We want to convert into horsepower, so we're going to multiply by a factor, or I guess divide by a factor of 550, which is horsepower per pound force per feet per second. So we get about 22.7 horsepowers. Okay, so that's the power required by the pump. However, once again, keep in mind, our pump is working at 80% efficiency. So what we calculate actually is the theoretical power of the pump. If we want to get the actual power of the pump, we got to divide the theoretical value by the efficiency, because therefore the real value will be a higher value, because we're going to put more power, and then with the efficiency that basically reduces the power, we'll have enough to basically complete the job that we want to do. So 22.7 horsepowers divide by an 80% efficiency, so 0.8. That is equal to 28.4 horsepowers. That's the power that is required to drive the fluid, the water, from the reservoir to your machine. Any questions on this? Okay. If not, last two problems, and we're done. Last two problems, we're switching the topic. We're going to look at vector fields, velocity fields, and basically the differential equation for fluid flow. So to kind of like, instead of the integral view or representation, which is shown in Reynolds transfer theorem, we're looking at the differential version now, which will lead to Navier-Stokes later on. Okay, so under what conditions does the velocity field V, given by this equation, does this represent an incompressible flow that conserves mass? Okay, so quickly just mentioning, I think back in Math 22B, differential equations, maybe even 2021D actually, but so we have position vectors, which are represented by S, maybe P or R, one of these three. And this is, either if we give it components, X component, Y component, and Z in the Z component. This would give us your location within a certain scalar field. So I drew a scalar field here. It'd give us your location, where you are in the scalar field. And there would be like an arrow pointing to, because the vector, to where you are in this field. Okay, so when we look at, when we derive S, P, or R, we get our velocity vector, which is represented by U in the X component, plus V in the Y component, plus W in the Z component, sorry. So if I draw that field again, an example of this could be, for example, your fluid flow looking like this maybe. So essentially, given your location on this vector field, you follow the velocity vector to your new location, then follow that new velocity vector to your new location, and just keep following that velocity field vector to wherever it leads you. And you get the velocity derivative, that's kind of like the scalar field, or the vector field you get, and that's how it works for velocity. Okay, so we're interested in figuring out how to solve this vector field in order to represent an incompressible flow that conserves mass. Okay. So we know mass conservation based on Reynolds transport theorem. Now we're going to look at the differential version of that, and it's as following. The equation for conservation of mass is the differential of rho density u for x divided with respect to the x component plus differential of rho v in the y component plus differential of rho w in the z component. These three terms should equal to 0. So the derivation of each component with respect to its actual component should all become 0. And this, if we look at this, the problem statement, that's your u, the first term, that's your v, and the last term is your w. So those are your three terms that we got to plug into this equation that basically represents conservation of mass. We're gonna the system is incompressible, so we can actually basically say that density is constant no matter where you are in your vector or your scale, your field. And if we divide rho on both sides, they'll all cancel out because there's all constants. Quick thing to note is that if we were to look at each term on its own, you'd see it'd be density, which is kilograms per cubic meter, times the spatial derivative of your velocity, which is meters per second. So this following would occur. And what you end up with, actually, if you have to rearrange these terms, you get kilograms per second per cubic meter, which is analogous to mass flow rate per volume. So essentially looking at, it's kind of like similar to the Reynolds transport theorem where we look at the mass flow rate flux through a surface. You're looking at mass flow rate flux through a certain unit volume, essentially. So you can just think of it as that. Okay, we're back to this equation. So over here, all of our densities cancel out, so we're left with differential of u with respect to x, differential of v with respect to y, differential of w with respect to z. We're going to now plug in this equation here, given to us, into this new equation we have for conservation of mass. So we have differential of x of a1 times x, b1y, c1z, plus differential of y, a2x, b2y, c2z, plus differential of z, a3x, b3y, c3z, all should equal to 0. So in this first term, differential to x, any term that's not x is a constant, we basically delete. So we're left with just a1. That's just a1. Differential. Second term of our equation, we see we take the different z and x are constants. When we take the differential to y, all left is b2. And last term, differential to z, x, and y are basically deleted. We're left with c3. So the sum of these three terms in our vector equation should equal to 0. So as long as these three terms equal 0, we have you have basically a vector field that is following the conservation of mass laws in an incompressible flow field. Any questions about that? Yeah, I mean, it sounds like gibberish. I kind of get that. But as long as these three terms equal 0, you have a flow field that looks normal, looks correct. And I'll show maybe a better example, hopefully, with this next problem. So once again, we're looking at an incompressible velocity field, and we're given the velocity components for u and w. U is x component velocity, w is z component velocity. So we're given that u is a times x squared minus y squared, and w is b, but v is unknown, and we want to solve for v. So what would the form of the velocity component v be? So once again, return to that differential equation for mass conservation. Differential of rho u with respect to x, plus differential of rho v with respect to y, plus differential of rho w with respect to z is equal to 0. Incompressible flow, we cancel out all of the omega terms, or if we divide both sides, they'll all go away. So we're left with differential of x applied to u, a times x squared minus y squared, plus differential v, it's a known, respects to y, plus differential of w, which is constant b with respect to x, all equals 0. If you derive a constant, obviously it gets to 0, so this term goes away. When this happens, we basically turn from a 3D problem to a 2-dimensional problem. So this problem is now just 2-dimensional. And what I mean by that is like, yes, there's a 3D field, but if we look at a 2D cross-section, it's the same no matter which z you pick, essentially. Anyways, first term, derivative with respect to x. When I derive this equation, y is a constant, I basically delete it. I get 2ax. My v term I still don't know, so I'll keep it as just as so. Last term is 0, and then so equals 0. I'm not going to do separation of variables, so I'm going to separate my differential term here, and basically I can then solve for the ODE by that way. So move everything to the, or I move the 2ax to the right-hand side, and I multiply both sides by dy, and I integrate both sides, and what I get is v equals to, sorry, there should be a negative sign here. Negative 2ax, so this would be a constant with respect to y, multiplied by y, because now y is like a variable. And because we're doing differential equations, it's an ODE, we have a family of functions. So we gotta make sure to plus constant c, and this constant c can contain x, contain z, and contain time. Any spatial or time, basically, variables that is not related to y, or that's not y. Okay, so that's the equation for v. We solve for velocity component v. Any questions? Okay, if not, last thing I want to do is talk about these two things. So first up, if we were just, at the start of the problem, we're just given our u components, so our x velocity components. If I were to plot that on a contour plot, you'd see the following. The yellow locations, left and right of the screen, represents very high rightward velocity. Like just, it represents velocities going to the right. The top bottom surfaces, which are like dark blue, represents velocity going to the left. So you see a lot of velocity, like you see a lot of velocity going to the right, or heading to the right on the left and right sides, but top bottom side you see a lot of velocity going to the right. So with just this information, one thing you might envision is that these velocities are going to hit each other and just cancel out, or something along those lines, right? And also quickly note the blue section or the green section that makes that X shape. That's where your u velocity is equal to 0. So basically, the velocity is not moving anywhere horizontally, is what that green location represents. So exactly what's going on, and the only way to find out is if we solve for our v component, and if we combine the u component and v component together, we get the following vector field shown here. And this vector field shows us, partially shows us what we know. Left and right side, you see very high rightward velocity. Top, bottom, very high leftward velocity, as you see here. High rightward velocity, high leftward velocity occurring at these sides. What we see is the flow is turning. We see flow turning, essentially. The flow following these vector lines. The flow is turning. And this is due to the perspective we now get when we solve for the v component. And based on the flow turning, we can see that that x pattern from earlier, from the contour plot, where the horizontal velocity is equal to 0, because the flow has to stop and turn around, essentially. That's how we get the 0 sections for our u component velocity. Yeah, any questions about this topic or these images? I did use MATLAB. It took me like 5-10 minutes, something like that. Okay. If not, thank you for attending my discussion. You guys are free to go. And please grab a snack on your way out.